So focal spot, remember the entire disc is not the focal spot. The focal spot is the actual area of bombardment. And it's going to be determined by two things. One is the filament size. Really three things. Filament size and stream of electrons are not necessarily the same thing. All right, so you got filament size. That's usually, that's what we use to control sharpness or recorded detail and focal spot size. But the other is anode bevel. So the anode bevel is usually 15 to 17 degrees, okay? So it's almost vertical. The bigger the number, the wider the angulation it is. The wider the angulation we have, the larger the actual focal spot, and even larger the effective focal spot. I shouldn't have brought that down yet. What I mean by that is, if we have a filament here, we've got a stream of electrons that come across directly from the filament, and we've got an anode bevel that's at about a 45-degree angle, and we compare that to an anode bevel that's at a, say, 17-degree angle. And we follow this stream of electrons out. We've got a area of impact that's that big on the 17-degree bevel, okay? So which one's bigger? It's about 45 degrees here. This 45-degree, this is how big our area of impact is with the 17-degree bevel, and that's how big it is at 45, right? So larger, what do we call that? Actual focal spot. Actual focal spot, right? It's the actual area. It's been a minute, right? That's it. Okay, so that's your actual focal spot. What do we call the projected focal spot? Effective focal spot. Right, so we've got an effective focal spot that's this big off of the big bevel. We've got an effective focal spot that's that big off of the 17-degree. Okay, so the things that control your focal spot size that are inherent in your, in your electron stream is the angulation of the bevel. The steeper the angulation, the smaller the number, the smaller the focal spot, and especially the smaller the effective focal spot, right? So size of the filament, if we use a smaller filament, then naturally we're going to have a smaller area of impact and we're going to have a smaller focal spot. But what contains the stream of electrons that come across to? What might cause us to suddenly bloom from a stated focal spot to one that's maybe 2 or 3 times the size that it should be? Is that? Rotoring, right? Yeah, I kind of gave that away. Rotoring and overdeveloping our focal spot size, or our thermionic emissions, our electron cloud, can lead to blooming, and in that exposure, we lose sharpness or recorded detail. But what about permanent loss of sharpness? Even if we don't over-rotor, what holds the electrons together before we send them across tube? Focusing cup. Right, so failure of the focusing cup. Now our electron charge is just all over the place, and when we hit it with KVP, electrons just fly all over, right? So gross misrepresentation of our focal spot size could be due to that, right? Imperfections and blemishes and damage to our anode could affect our focal spot size, just a number of different things. So what we left off with talking about was the difference between the actual and projected focal spot. Because that angulation of the anode, our actual focal spot is much smaller than our projected focal spot. If our anode was at a perfect 45-degree angle, then what we would get is a projected focal spot the same size as the actual focal spot. But by using that steep angulation, we can get a smaller actual focal spot versus the, projected focal spot versus the actual focal spot. So what we call that is line focus principle. The actual focal spot is where the electrons hit the anode, as opposed to if the patient could see up into the X-ray tube, then what they would visualize is the angulation. So, you know, if you were looking directly on something, it'd look that big, as opposed to if it was angled, it would look significantly smaller. So the line focus principle is the difference between those two things, with the actual focal spot being the area of bombardment, as opposed to projected focal spot being what the patient could see if they were looking straight up into the X-ray tube. So it's used to maintain a small projected focal spot and increase sharpness of recorded detail, and still have a relatively large actual focal spot, so that the X-ray tube could withstand greater heat. And that's what they tell us anyway. You know, realistically, we're not shining a light bulb, right? So we can't really stream electrons, hit the anode, and then go through the anode and project an X-ray field, right? Makes sense? So essentially what we have to do, regardless, is we would have to have some sort of angulation on the anode. So, but since we have to do that, the smaller the angulation, the steeper that anode, the greater the sharpness of recorded detail that we have. We have a greater heat capacity. Remembering that we have three different ways to conduct heat, or to get rid of heat. One is conduction, one is convection, one is thermal radiation. And if we've got a large anode and we're using a small portion of it that we're rotating around and around, then we can conduct some of that heat across the face of the anode, and we have greater heat storage, heat capacity in our X-ray tube. So then we, you know, thermally radiate to the glass, and then conduct it into the oil, and then convect it out into the room. So it extends tube life with a greater heat capacity. So changing focal spot effects, off-focus radiation. So off-focus radiation, a couple of things. It's not the same thing as blooming. All right? It is, but it isn't. So blooming, well, off-focus radiation, definition of off-focus radiation is radiation that's created anywhere except for the focal tract. Okay, so you know, your first thought is going to be, well, blooming does that. You know, we got too big of a space charge, and we send it across the tube, and it impacts a larger area on the anode. And my answer to you is yes. We're not going to call that off-focus radiation. We're going to call that loss of sharpness or recorded detail due to blooming of the space charge. Off-focus radiation is where the electron travels across the tube and it hits the anode, and because it's traveling at a very high velocity, it hits the anode, it might bounce back towards the cathode. But what is the cathode's charge? Is it negative? It's negative. So it bounces back towards the anode. What's the electron's charge?
Negative.
Negative. So they're going to push against each other. What's the anode's charge? Positive. So it's going to re-accelerate towards the anode, and it's going to hit somewhere else, and it's going to make an X-ray photon in that somewhere else. Okay, that's off-focus radiation. Blooming, technically, yes. I'll agree with you 100%. But for testing purposes, that's blooming. Off-focus radiation is where we get that bouncing of electrons. So if you answer, you know, blooming on off-focus radiation, you're going to get that wrong. Even though you're right, you're still going to get it wrong, because for testing purposes, we're calling off-focus radiation just those bouncing electrons that are created, that create X-ray photons anywhere aside from the focal tract. Okay? blooming, something different, even though it's off focus radiation is something different. So, it has no effect on contrast or density, even though it, you know, if, all right, so let's say you're looking at a number of colors and you let your eyes go out of focus. You know, you start to cross your eyes. What happens to the appearance of those colors? Kind of get fuzzy and harder to distinguish, right? So the same thing can happen with contrast, but that's really due to a loss of sharpness or recorded detail. So now we're back to something similar to modulation transfer function. You got to have that sharpness to see the contrast. You got to have contrast to see the sharpness, right? So we're going to say that even though you might not be able to visualize it, because of a loss of sharpness or recorded detail, we're going to say it has no real effect on contrast or density. So loss of sharpness or recorded detail, focal spot size, increased focal spot size, has no effect on that. The Heal effect is, if you remember, the difference in intensity between the cathode and the anode end of the X-ray tube, and it's due to the filtration effect of the anode itself. So if, let's say, all this, you know, that down there at the bottom, the writing at the bottom, were to reflect the window where all the X-rays exit, in my hand, or better still, this were to represent the anode, then in order for X-rays to exit through this end, they're going to have to penetrate a portion of the anode, right? So naturally, the intensity coming out from this end is going to be less than the intensity going out of that end, right? Because what do they have to penetrate to get out over there? Nothing, right? So intensity is going to be greater at the cathode end of the X-ray tube than the anode end of the X-ray tube. So how we use that is we would put the thicker end under the anode or cathode end of the X-ray tube, thinner end of the anatomy under the anode end. So we're doing feet. Toes are down here, ankles over there, right? We're doing T-spine. C-spine end is over here, abdomen end is down there, right? Greater intensity going through more, you know, thicker tissue. The one thing about the anode Heal effect is that the further out it goes, the worse it gets. So if we were to count the center of our central ray to be 100% of the intensity that we want, then the anode end may be 120%. Now the cathode end may be 120%. The anode end may be 80%. Okay? You follow me? So that's with, let's say, a 40-inch distance with your collimators open all the way. Okay? So if you back up to 72 inches and you want to cover the same field size, what do? Collimate. Yeah, collimate. So what you're using is more of this portion of the X-ray beam as you back up. Does that make sense? Mm-hmm. So the anode Heal effect becomes less pronounced at increased SIDs. Okay? So again, it's kind of like a divergence thing. As SID increases, divergence becomes less significant. Anode Heal effect becomes less significant as well. The other thing is that the blur, inherent sharpness of recorded detail, is going to be greater on the cathode side. So you get better intensity on the cathode side, but you sacrifice some of the sharpness of recorded detail on the cathode side. Okay, so we just talked about all that. What time is it? Oh, okay. Let's do motion, since I already advanced it to motion, and we'll call it there, because we got to get. All right, so motion is, remember you got two different types of motion. You got involuntary motion, you got voluntary motion. Some things that you consider voluntary motion are involuntary, some things that you might consider involuntary or voluntary. You don't think about breathing, right? But you can control it, and therefore it is voluntary in most cases. disease processes may introduce involuntary motion, like Parkinson's. Anybody had a patient with Parkinson's that you had to do something on? And sometimes they just can't stop moving, right? So they shake a lot. There's two different types. And kids, everything a kid does is involuntary, pretty much. They have, anyway. So there's two different ways that we can control motion. With voluntary motion, it's good instructions, right? Good instructions. Certainly there's some effects with the machine as well, but good instructions primarily. Involuntary motion is all about exposure time. So how do you get to short exposure times? There's the law of reciprocity, which means you increase your MA and decrease your time, right? That's the law of reciprocity. Keep the mass the same. Remember, reciprocity just means give and take. It's reciprocal to arrive at the same mass. Increase MA, decrease time, and you can reduce involuntary motion. What about if you're phototiming? You don't control either one of those, really. So how can you reduce exposure time if you're phototiming?
Your technique.
Specifically
Mass.
what?
No.
Well, mass, if you up your
KVP, because it'll penetrate.
Bingo, right. So if, and it's not ideal, because you want to use a KVP that's pretty consistent within the range of the anatomy that you're shooting. But if you're phototiming, you have no idea what kind of technique to set. Primarily you don't have any idea what kind of mass to set. So you can't really use reciprocity, but you can increase your KVP, and it's your MA for the most part, unless you're using a falling load generator. And I'll get you to go back to Bouchon and look that up. If you increase your KVP, the MA is fairly well set. So the variable that's going to change is time, right? So overall mass decreases, but specifically time. So you increase your KVP and your phototimer is going to shut off quicker. What about portables? What kind of timers do portables use? Making y'all dig deep today. A lot of blank stares. It's what we refer to as a mass timer. So portables, when you set your technique on portable, they have a set MA station, 100 MA. So when you set your mass, actually what you're adjusting is time, right? So again, if you're shooting portable x-ray on a patient, what you need is to reduce motion, and the patient can't cooperate, then again, you would use the 15% rule, increase your KVP, decrease your time, decrease your overall mass, and in that case, what you're doing is you're decreasing your time. Okay, so you can use KVP to reduce time. You prefer to use reciprocity. Where you can't use reciprocity, you can, I'm kind of beating this to death because every year I get people arguing with me, well, KVP doesn't have any effect on time. Yes, it does. If you increase your KVP, you want to maintain the exposure, you have to reduce your mass. If you reduce your mass, specifically to reduce exposure time, well, to reduce motion, then the variable that you change is exposure time, right? 15% works. So the issue that you run into, again, potentially and theoretically, with using your KVP and fast image receptors is possibly the introduction of quantum. So motion, the main thing that will destroy your image, and you have fundamentally no control over it. You can give good instructions, you can use short exposure time. If your patient's doing jumping jacks in front of your image receptor, you're going to have motion, right? It's all on the patient. Okay. All right, so we'll pick up there next week. So when's our test? When we get done.
How much we have left? I'm just trying to get a rough estimate here.
This last one, probably two more.
weeks.
Yeah, 2 more lectures and then the test. Yeah, that question was, that face was because I was like, I have no idea. I don't know. Yeah.
Didn't mean it. I did mean it, I swear.
Go there for the vibe.
To make
Nathan, you know what they're serving?
I do not.
I did, it was an accident.
They've kind of kept me a little bit in the dark on this.
Yeah. I wonder.
I guess we'll find out.
I reckon so.
Probably chicken of some sort,
Yeah.
usually the go-to.
Right.